All right, folks, a fellow Facebook astrophotography, I don't know if I could get the words out, astrophotography group member had a question about their Dob and DSLR camera, go-to and balance and counterweight. So it was kind of a combination of all that. So big picture, their question was, and Chris, this is for you. You were the one that posted the question. And by the way, I could type this, I guess, but it would be somewhat lengthy, cumbersome, would be open to ambiguity. And this way, you can watch it several times, get your answer. Also, we'll have a few visual depictions that may help explain some of this stuff I'll talk about. So, Chris, you got a 10-inch Dobsonian, which obviously is an Alt-Az mount, and we'll get into that in a second. You just purchased a go-to kit. Basically, your question was, hey, if I add a DSLR camera to it, will it throw off the balance? Will my scope still be able to slew correctly? And after I slew to a target using my new go-to system, if I put the DSLR camera on it, will it throw the scope out of balance? Will it move the target out of my field of view? And will I have to slew the target back into my field of view? And if I do, can I just use the hand controller from the go-to system? So just verbally, I'll answer and then I'll explain why. Think about it. Actually, I'm going to do a little bit of visual depiction here. Someone on there answered no, it won't throw it out of balance. And honestly, that's completely wrong. The only exception would be is if your eyepiece, which I assume you're going to use to initially find the target, and your DSLR camera are exactly the same weight. Then the scope will still be in the same balance that it was before you put the camera in. But even when you take the eyepiece out and swap it for the camera, for that moment in which we've had the eyepiece out and we don't have the camera in, the scope is out of balance, right? And that's, in the world of physics, that's by definition. If you take a seesaw or a teeter-totter and we have some weight 1 over here and weight 2, or we can call them forces, we have a fulcrum and we've got some distance 1 and distance 2. Well, in the world of physics, the math says W1 times D1 equals D2 times W2, or W2 times D2. It doesn't matter. So if I change any of these values, either the distance or the weight, in this case we're changing the weight off the front of the telescope by swapping an eyepiece for a camera, then this equation is no longer holds true. In other words, we are now out of balance. So the fundamental, straightforward, in a nutshell answer to your question is yes, your scope is out of balance. So there was someone on there that said, no, it's not out of balance, and I'm not sure why they said that. And again, the only exception would be is if the eyepiece and your camera had the same exact weight, but even during the time in which we're swapping this, the scope won't be in balance, right? So F1 D1 equals F2 D2 is how that formula works. So after I swap my eyepiece for camera, will my target move inside my field of view? It will. Your 10-inch telescope has a very narrow field of view. It is not like a refractor that has a fairly wide field of view. That 10-inch, I've got the 16, and also it's a Dobsonian, so obviously it's a Newtonian scope, but I also have a 8-inch, and even in the 8-inch, and it's on a German equatorial mount, so the mount's different and all that, but the fundamentals of the scope are the same. It's a reflector, and even in the 8-inch, the field of view is, I won't say super narrow, but it's not wide like a refractor. But in your 10-inch, odds are that scope, all it has to do is move just a little bit, and your target will be out of your field of view. And don't forget, the field of view for your eyepiece in almost all cases is going to be bigger than the field of view for your camera. So let's say, in fact, I just imaged and processed the hamburger galaxy the other day, so I'll use an example. So suppose, and this will look like a little hamburger. So suppose in my eyepiece, of course it would be circular, field of view, I've got the hamburger galaxy. Again, this assumes I can see it. It's like 10 or 11.7 magnitude, but assume I can see it. Well, when I put my DSLR in there, it most likely is going to have a narrower field of view than my eyepiece will. And so any kind of movement, so suppose your target is off to the side here, and as I swap these weights, right, the weight of the eyepiece and the weight of the camera, as I swap these, there's a little movement in the telescope. It may very well take the target outside of the field of view of your new device, i.e. either a new eyepiece or a new, an imaging camera. And especially when we start talking about planetary, DSLRs, their sensors are pretty big, so their field of view is fairly wide, apparent field of view, that is. But planetary cameras, man, their sensors are really, really tiny. So if you zoom in there, especially if you're using a Barlow or something, and you put Jupiter or Saturn, right there, or even Mars, even as close as it is, centered in your planetary camera's chip inside in the middle of its sensor, i.e. in its field of view, and bump that scope, you're going to find that planet is not going to be on there anymore. Which is why it's nice to have a kind of an off-axis, what do you call it? Off-axis, I'm sorry, it's a mirror that hangs down in the optical train. It's similar to off-axis guiding, but I can use an eyepiece to center the target and not have to take my planetary camera out of the telescope. So, so your scope is going to be slightly off balance. There's a chance, high probability, that you will move that target out as you swap the eyepiece for the camera. And here's another thing that's important. The focus for your camera is going to be different than the focus for your eyepiece. In fact, my technique is when I slide my DSLR into my scope and I use a Batinoff mask to obtain focus, I lock that focuser tube and I don't let it move. If I have to take it out and put it in an eyepiece to find a new target or recenter the current target, I don't focus with the focuser. I take the eyepiece, and really, depends on what the target is. If I'm just centering the thing in the field of view, I really don't need really good focus to do that as long as I can see it. But if I have to focus, I just slide the eyepiece. Sometimes I use both hands, just ever so slightly in and out of the focusing tube to achieve whatever focus I need. Then I lock it with the set screw. Remember, there's a separate set screw that locks the whole focuser tube in place. The set screw I'm talking about is the screw or screws used to hold the eyepiece in place. So I will slide that eyepiece up and down to achieve the focus I need to re-slew and recenter my target, or even go to a new target. As long as I've already achieved focus for my camera, I don't want to change that focus on that focuser again. With the only exception is, after a little bit of time, there's going to be temperature changes and your optics are going to change their size, and your tube is going to change its length as it gets colder. Typically, as we image later in the night, the tube shrinks a little bit, as well as the other hardware on the scope. So yeah, there's going to be some changes there as you go from eyepiece and swap it for camera. Now, one could argue, and so, by the way, let's go back to your original question. So if it moves out of the field of view or out of the center of my field of view and I want to center it, can you use the hand controller to slew it back in the middle? Certainly you can. That's no big deal. And I'm assuming, based on your question, that your new go-to system will also track, because there are go-to systems that will slew to a target, but then it doesn't move again, and it will not track in lunar, solar, or sidereal rates. Some go-to systems, kits that is, will slew and then continue to track at a rate based on what you tell it in the hand controller or the target you told it to slew to. So for example, if I slew to the moon in my go-to system, the hand controller automatically commands lunar tracking rates because it knows I slew to the moon. If I slew to the sun, it is going to command solar tracking rates because it knows I slew to the sun. And then planets and anything else out there, it will just simply use sidereal rates. So will it continue to track? The answer is yes. But there's another whole aspect to this that I wanted to talk about to you, and that is backlash. I'm not sure if that's a term you're familiar with, but in a nutshell, I'll describe it. Your azimuth platform and your altitude axis are driven by motors, right? And those motors are attached to a little gearbox, and then the output shaft from that gearbox, which turns very slowly, is attached to a warm gear, most likely in your system. There's some drive systems out there that are belt driven, so it's not a warm drive, but most are warm drives. Even my Celestron Gem is a warm driven gear. And as you probably know, a warm drive is, dude, it's just a screw. I mean, it's a bolt with threads on it, right? Just like so, and here are the threads. And again, I'm not here to win any awards for artistry, but that's what we have right here, these threads. And as this warm gear rotates, these threads have the appearance of moving. You'll see them move across. That's the fundamental way in which a screw works. And this is what I call the driving gear. It is the gear doing the driving. And it is driving another gear, and I call that gear the driven gear. And in your case, suppose this is your altitude axis. You're going to have a big, it's almost like a flywheel, you know, a big gear like this. And I drew it circular. But right here, as you well know, you're going to have teeth on this gear. Just like so. So as the threads of the warm gear move forward, they press against, and I'm going to draw this a little bit bigger. Here's one of the teeth of the gear, this driven gear. Well, now my warm gear thread, like this, is going to move forward, contact the tooth, and push it. And that's what drives this whole thing. And that's what drives the altitude axis of your scope. And that, of course, would be in the vertical. If we lay this down flat, then the same thing happens here, and that's what turns your azimuth platform for your azimuth axis on your Dobsonian. Now, in a perfect world, and I'll draw this, redraw this, this is the big picture. And of course, there's more than one thread usually in contact with more than one tooth on that gear. Usually it's in contact with maybe 2, maybe 3 at most. Remember, this is circular. Well, that's, like I said, no awards for artistry. So maybe, certainly 1, maybe 2, sometimes 3 of these threads are pushing against the teeth of this gear right here. Okay? Now, check this out. What if this thing is tracking, so it's slowly turning? In fact, if you were to watch it with the eye, you won't even see the thing move. But suppose I get the hand controller, and suppose this is tracking to the right for sidereal rates, and I tell my hand controller, hey, I want the scope to slew just a little bit to the left. Well, watch what happens here. These these threads on the warm gear, which were moving in this direction, now the warm gear rotates in the other direction, and guess what happens? This thread, all these threads, start moving this way. So let's suppose after a second or two, my threads are now like this. Notice they are not in contact with the teeth. We've created a gap here, and we haven't closed the gap here. So these threads continue to move until now they make contact with the teeth of the driven gear, and sure enough, now my scope starts to slew in the direction I'm commanding it to via the hand controller. And if you're not familiar with this, and you get a scope, you know, I was familiar with very little of this when I first got my 16-inch scope. And so I'm trying to track, let's say, Jupiter in my planetary camera, and it's drifting a little bit off to the side. So I'd get the hand controller and I'd press the left button, and the planet didn't move. And I'd release the button, go, hey, what's going on here? I'd press it again, the planet didn't move. And then I'd go, well, heck, I'd hold the button down, not knowing that all this is going on. Sure enough, these threads make contact with the teeth. The azimuth platform starts turning. I see the planet zooming across the camera's field of view. And I go, okay, perfect, it's centered. And I'd release the button. Now, what happens when I release the button? Does the warm gear stop? No, it picks up normal sidereal tracking rates now, or whatever target we're looking at, the sun, the moon, or planets, it doesn't matter. But in this example, when I'm looking at Mars, it picks up sidereal rate. So it's moving this way because I got the button held, and as soon as I release it, it picks up normal tracking rates, and now it's moving this way. So let's draw this picture to where these things are touching the teeth. Here's one touching here, and here's one touching here. So now it's moving Earth spin to recenter the planet like I wanted it to. Then I release the hand controller, and now it picks up sidereal rates, and what happens? Well, this thread that was pressing against that tooth now moves its way over here, right? Now it's not in contact with any of the teeth. Meanwhile, what's happening? Mars is moving back out of my field of view. Why? Because the Earth is still spinning. And even though this is turning to compensate for that earth spin, the teeth, the threads haven't made contact with the teeth yet in order to drive the azimuth axis to counter that earth spin. So this whole concept of these gaps between the teeth and the threads of our worm gear, or the threads of we could have multiple gears touching each other, it depends on the drive system. But the point is, you have a driving gear and you have a driven gear. And gaps between the teeth or the threads or whatever the case may be, depending upon your mount, that gap is what we call backlash. Not the gap itself, but this whole concept that I'm describing to you is what we call backlash. Now, in theory, if you look at the threads of a worm gear, it's actually kind of triangular shaped as well, something like that, typically. Now, I could push the worm gear, and in fact, you'll usually find some sort of spring mechanism pushing this worm drive, and this is on some sort of pivot system typically, pushing the threads from the worm gear into the teeth as much as possible to close this gap. So in theory, I could put this sucker right inside here and get a perfect fit. But I have found, and most folks will tell you, and I'm not an engineer, but I'm sure there's one out there that would back you up or back me up when I say this, to get the best, tightest fit possible actually puts a lot of strain on this whole system, particularly the driving gear. And so that's why it's a spring, by the way, is so that as these torque forces vary and as slew rates vary and as temperatures change, etc., I can actually vary the amount of force that this spring applies on here. And there's a set screw in here, at least on mine, that I can adjust and increase that force a little bit. But I found when I really cranked it, because I wanted those teeth in there tight, I wanted to minimize backlash, but I found that when I slewed, and even when it was tracking on its own, I could hear it kind of clicking. And it was a buildup of pressure in here, and then a release, and a buildup of pressure. In other words, I was getting binding in here, which is not what you want. So you want that nice and secure and tight there, but not so tight that it actually is damaging the system or creating binding. So how can we minimize this backlash? And this is tied to your question, because suppose, just for a second, I'm going to draw this a little bit bigger again. Let's put some teeth down here. I hope I'm not killing you all with boredom. But let's put some teeth and let's put some threads. Let's put another tooth here and another one here. And again, no awards for artistry, but let's draw some threads here from our worm gear that's rotating our altitude axis, because that's what we're going to talk about, because that's what we put our DSLR on. That's the axis affected by adding a little bit of weight there. So suppose that this is the configuration I have right now, and these threads are moving in that direction, which are making contact with the teeth, and it's rotating my driven gear in that direction. And suppose I've got a telescope like this. So I'm looking at something to the southeast, and as it rises, assuming you're in the northern hemisphere, as it rises and approaches the meridian, my scope has to rise and follow it. So that's what's happening right here. So if I take off an eyepiece, and suppose my scope is in perfect balance, right? F1, or we could call it M1 for mass, or we could call it W1 for weight, it doesn't matter. But suppose F1 times D1 is the same as F2 times D2. In other words, about the pivot point of my scope, and of course on the dial it's back here, but for purposes of discussion, we'll leave it like this. Suppose I'm in perfect balance right here, and it just so happens that these threads are pushing against the teeth. What happens when I go, well, I want to put a DSLR on? Now, will I take off my eyepiece? So now what part of the telescope is heavier? Well, it's this end now suddenly becomes a little bit heavier. Now, yes, I have the clutches engaged and the drive system is engaged, and I can't push this thing to a target, but I still have little bitty gaps in here, right? So what's going to happen? This is going to want to rotate just a little bit, and it's almost imperceptible in most cases. Unless you look through your eyepiece, you'll see that target moving. But this whole thing is going to rotate because we took an eyepiece off. So what does that mean? That means these teeth that were against the driving threads now are going to do what? Rotate and move over here. In fact, this whole thing would continue to rotate were it not for the teeth striking the threads of my worm gear. And how far does it rotate? Only enough to move these teeth over, close that gap, make contact with the threads, and then it stops moving. Now this distance, I don't know, 1/100th of a radian or 1/100th of an arc. So I don't know. But it's enough that you will see your target move in your field of view. So are we harming the system? No. Are we about to put a DSLR on here and get it back to balance? Yes. But for a moment, it's out of balance, and your target, whatever it is you're looking at, and like I said, especially for planets, because planetary camera sensors are so small, you'll see whatever it is you're looking at, Saturn or whatever, it'll go, and in fact, I will see mine oftentimes completely moved out of the field of view. I have to put my new camera back on. It will rotate this back in the other direction, assuming the camera is slightly heavy, right? If I put a weight back on here that's identical to the eyepiece, then the scope isn't quite sure where to go, right? And we're going to talk about that here in a second. But usually when I put something back on the front, and suppose it's a little bit heavier than what I took off, then my scope will rotate back this way. The teeth move back until they touch, again, the threads of my worm gear, and my planet will move somewhere back into my field of view. And it's not always perfect. It'd be great if it could go right back to where I want it, but it never does. And so I get my hand controller and I fine tune it and move it back to where I want to put it. And I'll talk about in a second techniques to minimize that movement when you're swapping eyepieces or swapping eyepieces for cameras or heavier cameras for lighter cameras, etc. So I hope this is helping out so far. We're at 21 minutes, but hopefully it's worth it. And by the way, I am going to post this on YouTube, and it'll be on my channel, and other folks can maybe gain some knowledge from this. So you have an issue with backlash in your case because we're talking about weights on the telescope. You have an issue with backlash in the altitude axis on there. So here is a way to eliminate this problem to the max extent possible. And in the world of equatorial mounts, German equatorial mounts, and computerized German equatorial mounts, etc., they do this all the time because if there's a lot of backlash in the system, then the auto-guiding systems typically do not work. Because auto-guiding, remember, it centers up a guide star in the guide camera at position XY somewhere on the guide camera sensor, and it locks it in. And if that guide star begins to drift off that XY pixel, that XY coordinate pixel on that array of pixels in the guide camera, it will send impulses to the mount to correct and slightly move to get that guide star back where it belongs. Actually, to not even let it drift at all. But if there's backlash in here, can you imagine being slightly off here as we're tracking on an equatorial mount, and then the guide software sends a pulse here to make a slight correction, and the worm gear goes, okay, let me move this way a little bit per that input from the guiding software. Well, guess what? The mount never moves. Why? Because of this backlash. All the impulse correction from the guiding software did was just open up a gap between the threads and the teeth. It didn't move anything on the mount, and guess what? Now the guide star continues to drift off target. The guiding software will recognize that, and when it gets to certain tolerances, it just says, hey, I quit, and I'm not even going to attempt to guide anymore. So in the world of guiding, backlash is a really big thing. So how can we minimize this problem? Well, here's how you do it. You make one end of your scope or the other heavier, and keep it that way. And that doesn't mean we throw a 10-pound weight on here from the gym. But what we do is keep it heavier so that if I even remove an eyepiece from the front is still heavier. And it's hard to explain, but in fact, I'll draw it here real quick. Do I keep the front heavier or do I keep the back heavier? And when you start getting into imaging, especially with, again, equatorial mounts, they always keep the east side of the mount heavy and the front end of the scope heavy. Some will make the back heavy, but they will always keep the eastern side of the scope, whether the telescope, the mount that is, whether the telescope's on the east side, we make this telescope side heavy, but then as we come past the meridian, they want the counterweight side to be heavy. And a lot of folks will get up just prior, if they're sleeping during imaging, they'll get up just prior to meridian flip, and the programming software will tell you just about when that target hits the meridian. They'll go out there and they will sometimes manually do the meridian flip themselves, but they will certainly change the weight configuration so that the east side of the scope is always heavy. So if you're looking south, again, this assumes you're in the northern hemisphere. If you're in the southern hemisphere, let's just say you're looking north. But for the generally speaking, things are going to rise from the east. They're going to arc. They're going to hit the local meridian for your location, and then it's going to set in the west. So a Dobsonian mount, in other words, an alt-az mount, the altitude axis is rising as this happens, and of course the azimuth axis is moving to the right. But once it hits the meridian, then your altitude axis starts going down. Starts going down. So this big picture of this gear I drew earlier, that shows a rotation this direction to raise my scope as I'm tracking the target up to the meridian. Well, guess what? When it hits the meridian, now it starts rotating down the other way. So you can imagine if we don't do anything and these teeth, the warm drive now starts, it was moving the threads in that direction. Now it stops and actually pauses right as the target hits the meridian, right? If I don't have this heavy on the nose or heavy on the tail, then the scope's not going to quite know where to go because there's this empty gap here that is not sure what to do. Finally, the warm gears start moving in the opposite direction because remember, my target is past the meridian. Now it's descending, and we're going to drive. Now our driven gear is going to go the opposite direction. Well, now that these threads make contact with the teeth, and now it's driving it down. So generally speaking, the direction that the scope is being driven, you want to have slight weight against that movement. Let me repeat that. The direction at which the scope is being moved, you want a slight force countering that move. Now again, I'm not talking about going to your local gym or going backyard and getting a brick and duct taping it to the front of your scope. It's just enough weight so that this gap is always closed. Always closed. So if we want to go counter to the movement of the scope, looking back at our horizon, here's south, here's west, here's east, here's our little, suppose we're going to image a star tonight, and it rises. Well, and here's the meridian, now it sets. Well, my telescope is rising to follow this up, so I want a slight force against that rising. So I want it to be nose heavy. I call the front of the scope nose. In the world of aviation, you call it tail heavy, nose heavy when you're talking about center of gravity and weight and balance, etc. So I want this front of this telescope to be slightly nose heavy. Hits the meridian, it's kind of a no man's land. Professional astrophotographers actually will avoid imaging here because the scope's not sure where to go. We're about to have a full-blown meridian flip, so we have to stop imaging anyway. And many of them will not image during this period, or they'll go out and they'll tell their system quit imaging, let me do a meridian flip manually, or just let the system do its thing, settle down, take out the backlash, and then start imaging again. And you can program software to do all that for you, by the way. But in any case, you and I don't have that fancy stuff with our Dobs. But now that the Dob is past the meridian, so has the target, as the Dob tracks the target, well, now the Dob is what? It's being driven down. Remember over here, the axis, your altitude axis was driving the scope up, so we wanted to add a slight weight to the nose to create a force down. Well, guess what? Now the scope is being driven down, so we want a slight force against that. And how do we do that? Well, we add weight to the back on that. And because remember our pivot point's here, so if I add a little force to the back end, it will want to force this nose up, and of course it can't because the teeth are against the warm gear. But the purpose of this, adding these slight weights, is to keep the gap at zero against the threads versus the teeth that are being driven. And remember that those threads moving this direction, when it hits the meridian, stop, now they go this way. And that's why I want to change the weight right here. So I may go out as soon as sun sets and there's a target in the east and I'm imaging it, or even looking at it. I don't even have to be talking about astrophotography. I want to look at it. I want to swap eyepieces. I want to be able to, my wife comes out and goes, I can't see it. Well, I swap eyepieces for her to a wider field of view, and it has better light gathering, more clarity. Well, when I swap that eyepiece, I don't want to put the new one in, and she says I still can't see it. And then I look and I go, well, I can't see it either because the thing moved, right? So if it's in the east, my axis is rising, my scope is rising, approaching the meridian, I'll have a slight counterweight on the front. And I'll talk about what I use here in a second. But when I'm past the meridian, in other words, I'm imaging or looking at stuff over here in the east that's rising, then I go, oh, hey, let's go look at M42, the Orion Nebula, and it's over in the west, and it's setting, approaching the horizon. So I slew my telescope over here, I stop, I take that small counterweight that was on the nose, and now I put it on the tail. Because now, as soon as I pass that meridian, your hand controller, by the way, your hand controller is where all the computer stuff is at. There's some controlling cards and stuff like that in your gear system and where the driving motors are. But your hand controller is the brain. So the hand controller knows now I passed the local meridian for the coordinates that I entered in and my elevation. So now it's going to reverse the warp drive in the other direction to track an altitude. Again, we're talking about an alt-as mount, Dobson mount. It's going to reverse those those threads in the other direction. So I want to go now tail heavy on here. So what do I use? Well, if you go to Harbor Freight or a welding supply shop, they sell these magnets, and they're like at 90 degrees or something like this. Yeah, something like that. It's 2 plates of metal with a ferrous magnet in between. And here's the body of my scope, and mine is metal. A lot of it's aluminum, but there's parts on it that are metal, and this thing goes clunk right onto it. They're lightweight, they don't weigh much, and I don't put them on here and move them around because I don't want to scratch my scope. If I had heavier ones, which I don't need because they're big enough for a 16, 16-inch scope, I'd probably put little felt pads underneath or something like that. But I put this, and here's my pivot point, I put these things, and of course, relatively speaking, it's only about that big. I put it on the front of my scope, and it makes my scope slightly nose heavy, whether I take an eyepiece out or not. If I take a heavy eyepiece and put in a small eyepiece, the whole time my scope remains slightly nose heavy so that I don't have any gaps between the threads of the warp drive and the teeth of my driven gear. Then as I get to the meridian or past it, then I'll just simply take this thing, I got to give it a little bend to break that magnetic force, and then I just stick it on the back here. And of course, remember our formula is F1D1 equals F2D2. So if I don't need that much weight on the back for some reason, then I don't need to change the weight. I just change its position because remember I can affect the distance or change the distance and still affect, this is called moment, by the way. I could still affect the moment or the rotational force applied to the scope by changing the distance. If I don't need much weight on the nose of my scope, I could put this magnet, let me get rid of this big picture of it. I can put this magnet way out on the front here. I can put it just halfway, on one of the truss tubes or something like that. Or my upper OTA, I can put it on the back end of the upper OTA. And I've got 2 of these things, so I can add another one if I need it. So that's how I keep my scope nose heavy prior to the meridian and tail heavy after the meridian. So in your case, if you were to use that technique, let's go back to your original question. That is, I've found a target, it's in my eyepiece, now I want to put my DSLR camera in there. Let's draw our little Dob telescope. Remember, we're only really talking about the altitude axis. Here's our eyepiece. Over here's our little camera with our T-mount. If you didn't do any of this and just did it the way, honestly, most people do, we would take out the eyepiece, it changes the weight of our scope, and if it happens to stay nose heavy, then we're okay prior to the meridian. But it may not be. A lot of people will want to balance this thing perfectly because they think scopes work better when they're perfectly balanced, and the truth is they don't. They work better when they're slightly imbalanced, and we discussed where to put that imbalance, right? Prior to the meridian, after the meridian. So I've got an eyepiece here. I take this off, and my scope is in perfect balance. I take the eyepiece off. Now the scope is slightly tail heavy. It rotates until those teeth move far enough to close the gap on the threads of the warp drive, and it's very little, but it's enough to move the target, most likely, certainly off center, and most likely out of the field of view of your eyepiece or your camera that you're about to put in there. So now I put my DSLR in here. the scope rotates back, and typically it won't rotate further than it was before, but it rotates back, and hopefully my target's back in there. But like I said, a lot of times it won't be. Most of the times for me, I do all this stuff, and sometimes it's still not in there. So I can imagine in your case, you'd probably lose it. So I swap this eyepiece out from my DSLR, and boom. Hopefully it's still there. If you use the technique I just talked about, in other words, keep it nose heavy while you're looking easterly prior to the meridian. So here is our eyepiece, here's our camera down here, and I got one of those little bitty welder weights here. So I have the combined weight of the eyepiece, and of course the tube itself, everything forward of that pivot point. But here's my little magnetic welder's weight, and you could use something else out there if you don't have anything that's got iron in it that you can attach this to. You could use a small weight and Velcro. You could have a couple strips of Velcro on the upper forward, what's called the upper OTA. If you don't have a full OTA, full tube, if you've got truss tube scope, the upper portion is called the upper OTA and lower OTA. But you could use Velcro strips. But the point is, I've got my weight here and my eyepiece, so I have a pretty good force, a combined force from both of those pressing down on the nose of the scope, countering the movement that the alt axis is trying to do, the altitude axis. And remember, that's what we want, because we want to keep those teeth constantly against the driving threads, just like that. We want that gap zeroed out. Well, guess what? When I take off my eyepiece, this force now is decreased a little bit, but it's enough to keep the scope from tilting. It's enough to keep the scope from tilting. Now I put my camera on here, and nothing changed in this picture. The driving threads were always pressing against the teeth, no matter what I did to this configuration here. And now, as my scope goes past the meridian, now it's being driven down. Now I want to slightly, so let's point our scope now in this direction to show that it's now pointing over here in the west. Now my counterweights, now I'm not talking about, you've got your normal counterweights here. These are counterweights to fight and compensate for backlash. So now I've got my welder's weight on the back here. So if I have an eyepiece here, remember this, I want this tail now slightly heavier, so the force driving the tail down will be greater than the force driving the nose down. Well, when I take this eyepiece out, this force actually goes down, right? Because I've lost some weight off the front. I still have the picture I want. The tail is still heavier. Now when I put my DSLR on, which is typically heavy, a little heavier than an eyepiece, as long as this rearward downward force is still greater, then I'm good to go. And this is why sometimes I have a couple cameras that are fairly heavy. When I know I'm going to be using them, I always use my second welder's weight on the back here to ensure that this downward force vector is always greater than the one that's going to drive the nose down. So that's what are we at? We're at 30, I can't read that. 38 minutes for that explanation, but to me, I think it's worth it, and I kind of enjoy explaining stuff too, and hopefully you won't be the only one out there that could benefit from this discussion. So, bottom line is, good, awesome you got a 10-inch, awesome you're going to throw a go-to kit on there, and awesome you're getting into astrophotography because you're talking about throwing a DSLR on there. But, to answer your question, will it throw it off balance? Yes, and we show how that would happen. Do you have an issue, or will you have an issue with backlash? Yes, everybody does, but we do things and have techniques and fine-tune our drive system to minimize that backlash as much as possible and its effects on our visual astronomy or astrophotography, and we talked about techniques to do that. Will it slew it out of the field of view of your eyepieces and or your camera? Yes, especially a planetary camera. It most likely will. It won't always do it, but most likely will. And can you slew it back with a hand controller? Certainly. Do that after you've changed your configuration, then slew it, because it doesn't make any sense to recenter that target and then change something on your scope and have to do it all over again, right? And that's, by the way, where a great Telrad or a finder scope comes into play. I use a 50mm finder scope, wide field of view with crosshairs in it. So if something moves out of the field of view of my eyepiece or my cameras, I can always use my finder scope, assuming I can see it, to recenter that target, namely like planets or even stars and things like that. And will it continue to track? Yes, it always will track unless you tell it to turn tracking off. It is always tracking. Even if you move the thing around, if you disengage your clutch assemblies and move your scope, it's keeping track of where you're moving it, and you re-engage your clutches, it will continue to track in sidereal, lunar, or solar rates based on either what you told her to track at, because I can go in there and change them manually, or based on the target type you told your scope to go to, it will still continue to track at those appropriate rates. So Chris, hope that helps, and anybody else out there, I hope that helps. If you found this useful, informative, I'd ask that, hey, subscribe and click like. And if you got questions, I learn a lot. I learn just as much from questions as I do reading other folks' posts and looking at their images and looking at their YouTube videos. So I learn a lot simply just by answering questions. It forces me to do research and get into the books too and explore some of the limits of my equipment. So subscribe, hit like, post questions, comments, etc. And I appreciate you guys watching. And Chris, man, I want to see some of those photos. I called you Chris. I hope, Christopher, that's okay. I want to see some results of your new system. I'm excited for you. All right, folks, take care.